Okay, so thank you very much for the introduction and the invitation. It's a pleasure to be here and to be celebrating Jeremy's birthday, whose ideas have inspired a lot of my work, as I'm sure you'll see here. So, okay, so let's start with describing the model. It's the colored ASEP. There are many equivalent names for this. I mean, one often uses the term multi-species ASEP. It was introduced around 40, 45 years ago, back in the works of Liggett and Harris as a very basic extension of the standard ASEP. So each site of the integer lattice is going to be occupied by a particle with some integer color. You should think of this color as a priority or a species. And particles will try to jump to the left and right at rates q, which you should think of as between 0 and 1 respectively. So you have an overall drift to the right. And jumps are suppressed if a particle of a lower color, a lower priority, tries to jump onto a space occupied by a particle of a higher color or priority. Okay. So here's an example of a. All right. Oh, yeah, I can see it now. Here's an example of a state. Okay, so you have some particles in the lattice, and they each have a color, which I'm denoting by some integer. And here's an example of some jumps. So here you should think of as j as bigger than I. So j can jump onto so j can jump onto I at some rate, at some rate 1, and j can jump back to the left onto I at some rate q. Okay. All right, so the system has a ton of information in it because each particle has its own species, and there are a bunch of ways to project onto other models. Maybe the most basic kind of projection is onto the standard ASEP. So you can fix some integer x, say 0, and you can think of all particles with species or color at least x as a particle, and everything with color strictly less than x, so negative, will be a whole. So then this thing will just directly project to the standard ASEP, the colorless ASEP, so to speak. Now, if you vary x, so I can do this projection for each value of x. I get many colored ASEP, sorry, many uncolored ASEPs, so many standard ASEPs, and they're all coupled together because they're all kind of secretly you kind of secretly have these colors that are telling them when they can and cannot jump. Okay, so these are a bunch of so that you can think of the colored ASEP as a bunch of uncolored ASEPs that are coupled together under a coupling that's called the basic coupling. And I've talked about, I just mentioned the projection onto a single species ASEP. You can also project in a similar way to the multi-species, two species, three species, et cetera, by thinking of colors bigger than 10 as particles, bigger than between -10 and 9 as second class particles or lower priority particles, and then all the other ones as wholes. Okay, so this, as I said, you can do various projections onto a bunch of particle systems that have also been well studied. Okay, so this system has a height function, which is defined as follows. So x, so it takes in 3 parameters, an x, a y, and a t. So t is always going to denote time. I'm going to be calculating at some time t. And it's going to just by definition be the number of particles of color at least minus x. It's a little for me to say, scaling up the theorems to have a minus here, that are at site at least y at time t. Okay, so this is just counting the number of particles of at least of a given color past a certain site at some given time. Okay, and of course, if I put all this information together, overall x, y, and t, I can recover the motion of the ASEP, the colored ASEP. Okay, so I'm going to be interested in scaling limit questions. So I'll start with some initial data. This initial data can change later on, but just to make things concrete for the moment, I'll start with what we call the packed initial data. So just at site. Okay, so at site 0, I have 0, and at general at site I I have a particle of color minus I. Okay, so if I do the projection, if I think of all particles with non-negative color as just a particle and everything else as a whole, this is the step initial data, and you're kind of coupling together a bunch of steps. Okay, and then you run the height function. It will start out on the left over there. It will be like an affine function, piecewise affine function. And then as you run it, it will start to evolve and curve. And we're interested in, as many of us are here, in the fluctuations of this height evolution over a long period of time. Okay, so the theorem, which is joint work with Ivan Koren and both of whom are here, is that you take any q that you like, and the statement is that this height function h under the KPZ scaling. So if I scale space by n to the 2/3 time by n and the fluctuations down by n to the 1/3, this will convert to a limit called the Airy sheet. Here is a somewhat more precise statement. So I have my height function. I'm looking at colors that live on the scale n to the 2/3, and that's corresponding to the fact that, you know, you can think of the initial condition, you're kind of looking on scale n to the 2/3 there. I'm looking at a space, I'm going to probe sites around n to the 2/3, and I'm going to look at time n, but then there's this constant in front. I subtract away a constant, and then I divide out by n to the 1/3. This will convert to a scale limit, which we'll call sub xy. This is called the Airy sheet. It was introduced by the Ortman and Virag about 6 years ago. In the context of random metrics, I'll describe it on the previous on the following slide. Okay, so this is a theorem statement, basically, that it's basically a theorem statement for the spatial scaling limit, both as I vary the colors and as I vary the site at which I'm probing, this is the spatial site at which I'm probing for the colored ASEP. Okay. So the statement, there are a number of corollaries. I mean, I can say them as extensions, but they're actually just very corollaries of the theorem, just a few page proofs. The first is that this is I'm not varying time in this theorem, right? So x and y are moving in this theorem. So this is like a functional scaling limit in two parameters, x and y. So I'm varying the color and varying the position I'm probing. I'm not varying time. You can vary time as well. You'll get a space. You'll get a space time scale limit, and the limit that you'll get is the directed landscape. You can also cover general initial data. This was restricted. The statement is for the pact, but you can in general access basically any initial data, and you'll get a bunch of KPZ fixed points that are coupled together through the directed landscape. And the third corollary is to the stationary measure. So these colored ASEPs, a lot of the work over the past several decades has not been about dynamical statements about the ASEP like this theorem, but actually just the stationary measures, which are fairly complicated for the colored ASEP. For the standard ASEP, they're just Bernoulli, basically. I mean, discretization of Brownian motion. For the colored model, they're much more complicated. A consequence of this theorem is that it allows you to basically pinpoint the scaling limit of the stationary measure for the colored ASEP. It converts to a limit called the stationary horizon, which I'm sure Timo will talk about in a few days. So anyway, these are quick corollaries. I'm not going to talk about them much or at all, really, for the remainder of this talk. I'll mainly focus on this theorem. Okay, so I will next try to quickly explain what this S is. So first of all, I'll explain where it arose in the context of random metrics, and I'll also try to describe I'll try to explain how it's described, basically. So let me first describe what it's a scaling limit of. So there's a scaling limit of a last passage percolation. So let's say I have some functions f. So I'll call this bold-faced f as a collection of functions f1, f2, etc. And you should think of them as real-valued functions that live on the reals. Okay, and we'll call the LPP value of f, I'll say from yk to x1. So the second index is kind of telling you which f you're looking at. And the first index is kind of you're going from some say point y to some point x. So I imagine like I'm going from the k. So okay, maybe you should think of this as k. So I'm like going from ky down here to x1 up here. So this is basically I look at all possible paths, piecewise constant paths from basically from yk to x1, and I'm going to look at the increment of the sum of the increments of the fi along these paths, and that's going to give you your FPP problem. Okay, your LPP problem. Okay, so Brownian LPP is the case when this f is just a bunch of independent Brownian motions, and there's been various work studying the scaling limit of this object, and key ideas which go back to Johansen for the discrete version of this model, and Baryshnikov, Grafner, Tracy Whittam, O'Connell Yor, Bergerov Dolan, and there's a long list of people that happened around the turn of the millennium. They use the RSK correspondence to match this LPP value or this LPP problem under this Brownian noise to the edge limit of random matrices and deduce KPZ statistics. So this S is basically simply the scaling limit of this S as a limiting object. It's the scaling limit of this Brownian LPP. So basically, if I look on n, if I look on layer n, and I look on kind of a spatial scale of x times n to the 2/3, so I kind of vary my starting point down here. and I vary my ending point up here. I subtract away the expectation, I divide that by into the 2/3. As I vary x, like sort of x and y, I'll convert to a scale limit called S of xy, which is the Airy sheet. So this is how the Airy sheet was originally defined as an LPP problem. Okay, now in order to, okay, that's telling you what it is as a scaling limit. In order, so you might want to actually know how to define the object. So it's actually, it would help for me both for now and to kind of explain issues that will arise. Explain, maybe not just give you a formal definition of it, but kind of give you a sense of how this is proven, because the proof will actually basically tell you what the Airy sheet is. Okay. So the RSK map, as I mentioned on the previous slide, is a fairly fundamental object. I'm sure the next talk by Duncan will talk about it in much more detail. But basically, one consequence of the RSK correspondence, if you look at it fairly carefully, is it maps Brownian LPP to LPP, but with a different family of Fs. Okay, and the family of Fs that you can use instead are the curves in Dyson-Brownian motion. So I start out with a bunch of Brownian motions starting at a point. I run them and I condition them to not intersect. That will give me Dyson-Brownian motion, which is a family of non-intersecting Brownian motions. So over here, okay. And the claim is that basically, from the RSK correspondence, if you look at last passage paths across, like the last passage values across these independent Brownian motions, that's equivalent to looking at last passage values across the Dyson-Brownian motions. You can kind of, in a sense, swap out the Brownian motions, independent Brownian motions, with the curves of Dyson-Brownian motion. Now, at first glance, this might not seem great because I originally had noise that was nice and independent, and what you're doing is you're swapping them out with Dyson-Brownian motion, which is extremely correlated. Okay, but the value of doing this is that only the top curves are relevant for the fluctuation. So what will happen is that only the top, 1,000 curves, you'll get very close to the actual LPP value if you just take those curves into account. Now we know, so basically it's only the edge of the Dyson-Brownian motion that matters in the limit. So the edge of Dyson-Brownian motion, we know what it converges to. I mean, you have many formulas that will tell you what it converges to. It will converge to the Airy line ensemble, which was first introduced by Brohofer and Spohn at the level of finite dimensional distributions, and then by Corwin and Hammond as sort of continuous processes. So if you believe what I said, if you want to understand the scaling limit of Brownian LPP, it turns into the scaling limit of LPP across the edge of Dyson-Brownian motion, which is the Airy sheet. So you can imagine that Dyson-Brownian motion converges to an LPP across the Airy line ensemble, and that's more or less the definition of the Airy sheet. I mean, you kind of have to make sense of this, but it's more or less an LPP whose Fs, basically, whose noise is given by the curves of the Airy line ensemble. So I should say that this work needed to obviously make this precise, but my goal in this slide was to give you a sense of what the Airy sheet is. Okay, so so this RSK correspondence is fairly useful for analyzing other last passage percolations in polymers. For example, the work of Davern, Nick, and Barag analyze various other LPP models such as Poissonian, exponential, and geometric. And Xuan Wu, who we'll also speak later today, talks about the KPZ equation, which is another polymer model. Okay. So for ASEP, though, I mean, the colored ASEP, the problem is that it's not a polymer or an LPP problem. And there's not really much of an analog of the RSK correspondence for not just ASEP, but just in general interacting particle systems like the ASEP. And in fact, sort of, if you were following the previous slide, the hypothetically relevant, like if such an RSK did exist, sort of the relevant output of it would be kind of an exact LPP or polymer, with glass passage percolation or polymer in some dual environment, which in the previous slide was Dyson-Brownian motion. Here, I mean, if something like that existed, it would be, you would be able to express basically ASEP in terms of some kind of glass passage across some environment. And this is simply not known for the ASEP. I mean, people have tried for around 3 decades by this point, but to come up with some exact glass passage interpretation of ASEP. And this is one of the reasons why ASEP is so much more difficult to deal with than TASEP. Okay, I should actually mention that even for colored TASEP, something like this had not been found earlier. Okay, so nonetheless, there are of course many results on the ASEP and its colored version. So the original results, I'll just talk about the fluctuation results. So the original results were 1-point convergence to the Tracy-Whittam distribution under the patch initial data due to works of Johansen and Tracy-Whittam 10 years later. Now, if you look at general initial data and look at kind of the full multi-point convergence, the full convergence, this is much more recent results, contributions of Jeremy and colleagues to the KPZ fixed point. So for the TASUP, it was introduced in the introduction of the KPZ fixed point by Vitetsky, Quastel, and Reminick. And for the ASEP, it was done by Quastel and Sarkar. And for the TASUP, it was done by exact formulas, basically. As Li Cheng said, you solve it to death. And for ASEP, you prove it by comparison. Now, for the colored ASEP, when you start putting species in, you're going to have a lot more of a difficult time computing. Basically, the determinable structure, much of the determinable structure, even for colored TASEP breaks. So we can't. So there have been many formulas, like just computing moments or trying to compute transition kernels. I've listed some of the relevant literature here. They've come up with formulas and stochastic dualities, but it's not known how to obtain asymptotics from them, even in the colored TASEP case. And instead, sort of the most fruitful way so far of proving asymptotic results have been matching results. So matching results to uncolored TASEP. So certain observables and the colored TASEP can be expressed in terms of observables of the uncolored ASEP. And since this bullet point over here, I mean these previous works say that we basically know a ton about the uncolored ASEP. You can use that to extract information about the colored ASEP. So one example of such a marginal, I actually kind of alluded to it in the first slide. I mean, just if you project and look at the height function for just project, think about all particles of color less than 0 as wholes and at least 0 as particles. That is one kind of trivial observable that projects to the uncolored ASEP. But they're much more involved and surprising ones. But they are kind of limited, and they kind of have to be limited. Sort of the information of the colored ASEP is much more rich. There are certain intermittent phenomena that you just don't see for the uncolored ASEP. So this matching can only apply to specific marginals, and you really, I would be somewhat surprised if you'd be able to get the full scaling one. Okay, so I should tell you how so I want to now try to explain how we prove these theorems. And to do that, we'll go through a different model called the stochastic six-vertex model. It's a model sort of its own, it has its own story to it. I mean, it's a descendant of the original six-vertex model, which is in fact much older than the ASEP. And I'll describe it as follows. So we have, the model will basically be, you have a bunch of colored arrows moving through a lattice with certain probabilities. Okay, now each arrow has a color, and that color will kind of be the priority of the arrow. Okay, so now the probabilities are shown over here. There's kind of a chart of them. So if I have two arrows that are coming at each other of the same color or the same species, they're gonna kind of bounce off each other with probability 1. So this is kind of forced. As you'll see in all these pictures, it will have the rule that arrows incoming have to leave. So you can view these arrows as paths in the system. Okay, and then I'll fix some parameters B1 and B2, and I'll let the ratio be Q. This is the same Q as for the ASEP. So it's kind of the asymmetry in the model. So the chance that if I have a color I meeting a color J, so that J is again J is bigger than I, so J is the higher priority color, is meeting the lower priority color from the bottom, there are two things that can happen. It can go straight up, or it can kind of bounce off. And these will happen with properties B1 and 1 minus B1. And likewise, kind of the reverse, J can go straight through horizontally with probability B2 and 1 minus B2. Okay, so these are stochastic dynamics for how to kind of evolve, how paths like locally evolve. Okay, so so you can look at uncolored versions of this model where all the I and J are just 0 and 1, or you can look at the colored version where I have many colors, many different I's and J, many different colors in the system. And they were introduced in the works of Guaxpon and in the uncolored case, and by Kuniba, Magajev, Moriyama, Okano, and also by Borden and Wheeler in the colored case. So I just want to quickly, I mean, so the stochastic property, the fact that this weight plus this weight sums to 1, and this weight plus this weight sums to 1, it allows you to think of this as a Markov process. So let me just try to make that a little bit more explicit. So I have some initial condition, say red is color 1, so red is so these colors are ordered by the frequency of light. So red is the lowest, yellow is the second lowest, green is the third, and blue is the highest. So you start out to say that the southwest vertex, and you see a red arrow coming in and kind of nothing coming out. And nothing you should think of as an invisible arrow of the least priority, so with negative infinity. So you see that we have kind of this situation here where J is 1 and I is negative infinity. Okay, so it can do one of two things, right? This arrow can go up or it can go straight through. And those happen with probabilities 1 minus B2 and B2 respectively. Okay, so let's say it goes straight through with probability B2. Again, I have the same options, and it can do something like that. Okay, then I see no action here, no arrows are coming in, so nothing can come out, and then I kind of just repeat this row by row. So, you know, this yellow can either go straight through or can go up. Let's say it goes up. Then again, I can look at this one. It can either go up or straight or turn. Let's say it turns and then it goes up, and then, you know, you keep on sampling this way. So this is a Markov process. Okay. Okay. So there are many reasons to study the stochastic vertex model. I mean, I've described a new model too. One reason is that you can study the colored ASEP through the colored stochastic vertex model. In particular, if you kind of there's a scaling procedure which I don't want to go too much into, but basically, if you set B2, so these weights, so these B1 and B2. So imagine that these are very small. So imagine they scale like epsilon. Okay, so then what will happen is that paths. If these B1 and B2 are very small, then this is the probability that, you know, the higher priority, like the paths go straight through each other. It's like just straight through motions. So if those are very small, then really the only option that will usually occur is that the paths will start to zigzag. Okay, but every once in a while, a path. So usually the paths will go diagonally, but every once in a while they'll kind of go one extra space forward or one extra space up. And this, if you kind of offset by the diagonal, under some scaling that's not so hard to justify, this will converge to the ASEP. So you can think of the ASEP, or the colored ASEP, it's just a scale, it's just a certain limit of the color stochastic vertex model. Okay, that's one reason to study it. You can also study it in and of its own right. It's an old model that's certainly very interesting. And here's a simulation for it. You can hopefully see that it's kind of pretty. And our results apply to it equally well. I mean, our results also apply to it. So the theorem will say that the color stochastic vertex model converges to the Airy sheet as well in the same way. I won't give you the formal statement. Okay, so now either way though, I'm going to restrict to. I'm going to just, as I said before, if all you care about is the ASEP, I'm still going to study it through the stochastic vertex model. So I'll be focusing on this vertex model for the rest of the talk. Okay, so the analysis, the way we analyze this colored stochastic vertex model is by embedding it or kind of matching it to a different model of paths. And this model of paths will no longer be Markovian. So in that sense, it might a priori seem a little less easy to study. But I'll try to explain as the talk progresses that this path that this model that I'm about to describe actually has a lot of structure in it, which we can exploit. Okay, so this model, it's called the colored Q-boson model. So it's defined by Boltzmann weights, basically. So this is now going to kind of be an equilibrium model instead of a stochastic one. So I have a lattice, and at each point in the lattice, I can have various paths passing through it. And depending on the local configuration at a vertex, I'll have a weight. Okay, and then I take the product of the weights, and that will give me the probability of seeing a given configuration. Okay, so the weights are shown over here. So let me just make a few comments about them. First of all, they depend on a parameter u. Okay, so these weights, I'll call them wu. Okay, and second of all, the difference between this model and the previous one, in addition to the fact that it's not stochastic, is that now many arrows can exist along the vertical direction. So many paths can kind of group along a vertical edge, but only one can go along the horizontal edge. Okay, I've given you explicit weights here. Those weights are not going to be extremely important. I've just written them to show that they're very explicit. A few things that you just want to keep in mind is, first of all, they do indeed depend on this u in a clean way. Second of all, they involve powers of q and powers and things of the form 1 minus q to some power. Okay, so that's all I'm gonna, for now, that's all you need to know. I mean, they're fairly explicit, but yeah, they involve u powers of q, basically. Okay, so now the color Q-boson model, I'll define it as follows. We'll let m and n be some integers, okay? And we'll set z to be something in terms of b1 and b2, okay? So I'm gonna, again, try to match the color stochastic vertex model to this new model, this Q-boson model. And the parameter that underlies the Q-boson model will be a combination of b1 and b2 that's written in terms of the z 1 minus b2 over 1 minus b1. Okay, and this is something between 0 and 1. Okay, so now the colored Q-boson model will basically, by definition, the lattice, the domain will actually be an infinite domain. So it will be, I should think of it as kind of the negative quadrant. So it's going to be z minus, so z less than 0. So this side times the interval 1 to n plus n. Okay, so this is kind of my domain. Okay. Okay, so what's going to happen is that a bunch of arrows are going to enter from the bottom according to some. So I have m plus n many columns. And at so at the ith column for I between 1 and n, I'm going to have an arrow color I entering. Okay, so an arrow color 1 enters here, 2 enters here, and 3 enters here. And if n is 3 here, that's it. Okay, so I have some arrows entering from kind of minus infinity. And now these arrows can move up and right, and they can kind of combine in columns if you like. And at the end of the day, I want them to all exit at kind of the top east corner of the rectangle. Okay. So so there are many ways in which this can happen, and each of these I'm going to assign a weight, which is simply the product of all of these weights. Now, the one thing I didn't tell you was what is the u? Okay, like these weights depend on u, and I haven't told you what u is here. So it'll be defined, if you haven't seen this before, it might seem somewhat unusual. So what will happen is that the first n rows will have u equal to 1, and the last m rows will have u equal to the z. Okay, so this is just maybe a somewhat, if you've never seen this thing before, it might seem somewhat contrived, but this is the definition of the model. And this will actually have a lot of structure that we'll be able to analyze, even though it a priori looks considerably more involved than just the particles jumping. Okay, so now the reason this is useful, I've just defined a model so far. I haven't told you what it has to do with the stochastic six-vertex model. And the reason, so what it has to do with the stochastic six-vertex model is that there's a certain matching result, which was, this form of it was proved in joint work with Alexei Bardin. So it states the following. Basically, if I take the stochastic six-vertex model, as I said, you could kind of think of it as being defined on a quadrant. Okay, so let's say I have some initial conditions where arrows are entering, colors 1, 2, all the way up to n. And okay, so now I run this Markov dynamic, right? As I said, I kind of start here and I see how they evolve. They're going to eventually exit this rectangle, this n by n rectangle, and some colors are going to leave in some order, right? So let me call the colors along these edges J1, J2, etc. So I'm kind of crawling around this thing counterclockwise. Okay, and I'm calling these the J's. Okay, so this is some, I get some random J's when I do that. So I can ask myself, what's the law of these random J's? What is the law of the exiting colors from this rectangle? Okay, and the statement that will allow me to link the cuboza model to the six-vertex one is the following. So let's say I take the same picture from the previous slide, and now all of these colors are eventually they have to leave over here, right? They have to leave to the rightmost column, right? So that means that they enter all of these paths, they have to enter the rightmost column at some points. So let me call the colors of the paths entering at the bottommost row J1, the second row J2, et cetera, all the way to Jn plus n. So now I have some other, this is again random, right? Because the way in which paths flow here is also random. So I have a random J here, some random entrance data, some random way in which they kind of exit the first column, the minus first column over here, and some way in which they exit the rectangle over here. And the matching statements is that these two J's have the same law. Okay, so the way in which the arrows exit here is the same in which they either, and you can think of them as entering the last column here, or exiting the minus first column here. So this is kind of a matching statement. It matches colors exiting the stochastic six-vertex model to colors exiting the minus first row, the row index, the column index by x equals -1 of the cuboza model. So in particular, it just suffices to say understand the scale limit of the ladder. So I just need to understand kind of the scale limit of this object, okay, which a priori might seem much worse, but I'll try to explain that there's a lot of structure here that's not at all apparent on the six-vertex or the ASEP side. Okay, so I should say the proof of this result is actually extremely quick. So if you know, it's a very quick consequence of the Yang-Baxter equation. If I have time, which I might not, I'll give the proof. It's actually just a slide basically. And previous special cases of this result were shown by Borden, Buffetov, and Wheeler, and Buffetov, Muchikoni, and Wheeler. So I certainly, I might owe you a proof of this relation. But I mean, I've introduced many things at this point, right? I've introduced a somewhat complicated model, and I feel I might be first obliged to explain what to do with it. How do you work with it? Okay, so I'm going to, before I do that, I'm just going to keep track of it in a pretty efficient way, which is in terms of a height function. Okay, so for each x and k, so you should again think of x as indexing a color, and k is going to be indexing a column. So I'm going to define a function, which is this lk at least x. So this is going to be a function on 0 to n plus n. So this is, I should view this index here as kind of a vertical coordinate, and k is kind of indexing a column, okay? And this lk, at least x of y, is kind of going to be something similar to a height function. It's going to be the number of paths exiting column minus k above. So if you exit column minus k, you have to exit at some y location. And you're just going to count those that exit strictly above minus ky under this Q-boson model, because it's just something that keeps track of all of the paths in the system. Okay. Okay, so I've drawn some examples over here. So the purple is L greater than or equal to 1. So this is actually, I have some red paths and some blue paths over here. So this is kind of purple is kind of keeping track of everything. Okay, so just as a quick example, if I look at minus ky and k is 0, sorry, if y is 0, so this is like your y, then all of the paths exit strictly above 0, right? I mean, they enter strictly above 0, so they exit strictly above 0. So this is actually just counting all the paths in the system. You have 4 paths here, so they all start at 4. And then they kind of, these height functions go down, okay? So this is kind of how L greater than or equal to 1 would look. This is how L greater than 3 would look. You have kind of 2 more, which I have not drawn. Okay, so these are equivalent. So if you have this picture, these pictures, you can reconstruct this picture. And the definition constructs these guys from this. Okay, so these incorporate the same exact data. There's no difference between looking at this thing in terms of these height functions or in terms of the model itself, or in terms of kind of the model itself. Okay, so we call this collection of height functions, we'll call it a colored line ensemble. So it's just like a family of like kind of tuples of height functions of these paths. Okay. And each of these L greater than 1, L greater than 2, et cetera, these all have a bunch of curves in them, where these curves, again, correspond to the column in which you're looking at. Okay, so again, the top index is telling you the color, the bottom index is telling you the color. Okay, so you can view this. So each of these guys is kind of a bunch of paths. You can think of them as a bunch of paths that always go down, and they're ordered. So I mean, the fact that they go down in order is kind of a quick consequence if you just think about this definition for a moment. It's not so hard to see. So so kind of an individual version of this is often what's called a line ensemble, which is a family of curves, sometimes ordered. What you have here is you have a bunch of these line ensembles, like one for each color, right? So they're all interacting in some way. Okay, so I can think of the colored line ensembles, basically a big family of line ensembles that all talk to each other. These fairly complicated Q-boson weights from my previous slide. And the previous, like my matching statement that I had mentioned tells me that, remember, color is exiting the -1 column are matching to the colored 6 vertex model. So really, if I want to think about the colored 6 vertex model, all I care about are the paths that are exiting column -1. Okay, but that's exactly the top path. Like that's exactly the k equals 1 case of this thing. So all of my colored 6 vertex model, everything I care about colored ASEP or colored 6 vertex model, all that juice is all contained in the top curves of these line ensembles. Okay. Okay, so now how are we going to prove the scaling limit? I'll kind of give you a rough sketch of how we'll proceed. Is that, again, these colored line ensembles, I think of them as many line ensembles all coupled together by these Q-boson weights. So the outline of the proof of the scaling limit will be the following, okay? So the first thing, there are kind of 2 things involved here. First of all, you have a bunch of ensembles, a bunch of, families of paths. And second of all, they're all talking to each other, okay? So I want to kind of separate these 2 issues in a sense. So the first step is to kind of identify the limiting coupling to see how this asymptotic coupling passes through the limit. And then I'm going to identify, what each one is kind of doing. And putting them together, I'll get the full scaling limit. So the limiting coupling will be the following. So what will happen is that I have many line ensembles here, one for each x, right? And what will happen, in fact, is that all of them are going to be approximately, and that approximate will be exact in the KPZ scaling limit, like kind of that error will go to 0. Is that all these line ensembles are actually just determined by one of them. Okay, so all these L greater than x's are determined by just L greater than or equal to 1. In fact, it's an approximate, you can think of them as approximate LPPs, approximate last passage percolations over just this one line ensemble. So what I'm saying is that this blue line ensemble here can be represented as a last passage percolation whose noise, whose Fs are exactly given by the curves of these L greater than 1. So you kind of already see, this is kind of already giving you what we were seeing in the definition of the Airy sheet, an LPP over something. So now I know how to determine everything from just this guy. So my next task would be to determine what just this one line ensemble is doing. So the second step is to identify the scaling limit of that L greater than or equal to 1, which will show convergence to the Airy line ensemble. So if you put these 2 together, first what you're saying is that all of these line ensembles are LPPs over just one of them. And second of all, that one converges to the Airy line ensemble. So putting them together, you'll get that these guys will all act as LPPs across the Airy line ensemble. And that's exactly how the Airy sheet was defined. Okay, so this is how you're seeing. So this is the advantage of the Q-boson. Although the kind of LPP structure was not apparent from the original ASEP through this, through this somewhat more, fairly more complicated family of line ensembles, you can kind of see it's not in an exact form. It's probably actually false in exact form, but in an approximate form. Okay. So let me at least try to explain a little bit of what's going on here before I have to finish. So to identify the limiting coupling, let me first kind of explain in a very quick sense how this works at q equals to 0. And it will actually be not so much of a conceptual leap to see this for general q. Right, okay. So the claim is actually at q equals 0, if I condition on the purple guy, so like the thing counting everybody, all the colors, okay? If I condition on L greater than or equal to 1, then I've determined it. Just deterministically, you found out what L greater than or equal to x is for any x. Okay, so I remind you that conditioning on L greater than or equal to 1 is fixing the arrows in the Q boson model, but not actually fixing what their colors are, because I'm only counting all paths of color at least 1, but I don't know which path is which. So the way I'm kind of conceptually drawing this is, I start with this L greater than or equal to one line ensemble. I have this Q boson model, and I know how the paths are entering it. And what this line ensemble tells me was what the arrows are doing, but it doesn't tell me what all the colors are. So I'm kind of just drawing them in purple. And my claim is that at q equals 0, I can distinguish what all the colors are. Okay. So I'll quickly tell you why you can do this on a conceptual level. So let me take a vertex. Let's say we start at the bottom here. Let's suppose we fix the colors of the incoming arrows, and we fix the number of outgoing arrows. So you think of it as I'm fixing the colors of what arrows come in, and I know how many arrows exit through the top or through the right, but I don't know what colors there are. So I'm going to try to draw them as purple. So the information I'm given is you can think of this or this, where I have some arrows coming in and I know the color, and I know how many arrows are exiting along each edge, but I don't know what the colors are. Okay, so the claim is at q equal to 0, there's just a deterministic rule. As long as, if I go back to these weights are explicit, and I can just plug in q equals to 0 and compute what they are. And I'll tell you the relevant rule here, which is that the horizontally, so I have some arrows coming in, and the rule is that the horizontally exiting arrow, if it's there, is equal to the largest entering arrow, the largest color of the entering arrow. So here it's kind of trivial, right? Because I have some arrow paths coming in, and I know that they all exit here. There's no choice, right? Everything that came in has to come out. So I have a unique choice of how to fix it here. Now for this one, I have 3 arrows coming in and 1 arrow exiting horizontally and 2 arrows exiting vertically. So I have a priori I have 3 possibilities. Any of these guys can a priori exit here. But what this rule is telling me is that it's the one that exits there is exactly the one of the highest color. So it's this dark blue. Okay, so that's like just a deterministic rule for telling me how to kind of, given the arrows coming in, given the colors coming in, how the colors escape. So you can imagine I start here at the bottom right. I see a magenta arrow coming in and nothing coming in horizontally, nothing coming in vertically. I also know what the purple arrow is, so I can use this rule to fix that it's magenta, and I can keep on doing this. I can kind of propagate this to fill in all the colors in the full system. Okay, so there's a deterministic rule for explaining how to recover the colors from just L greater than or equal to 1. So this is just okay. So that's a rule, because this is a deterministic way of revealing colors. And it's natural, to try to express that just in terms of the L's, in terms of the height function. And what you do it's not very difficult to do that. You kind of sit down and write for a page and you'll come up with the answer. And it turns out that that's exactly an LPP, okay? So with this, if you just unwind the rule from the previous slide, what you'll see is that it's exactly an LPP across the uncolored, the purple line ensemble. So this is in fact giving you kind of an exact dual representation of all of the line ensembles across the first one at q equal to 0. And I should say that I actually don't know how to recover this directly from RSK. So even at q equals to 0, this is some other kind of symmetry that's happening that I know how to see from the RSK correspondence. Okay, now this breaks when q is bigger than 0. The reason is that the statement is now false. So this determining statement is no longer true. So no longer does W non-zero determine how the arrows are exited, determine the colors of the arrows exiting a vertex. But if you remember, these weights had powers of q involved in them, right? And what's going to happen is that those powers of q are going to completely penalize you, are going to penalize errors from the LPP representation. So if this is too far, this will not hold exactly. But if it's too far from being true, you have a lot of powers of Q, and Q is less than 1, which will make it unlikely to see such a big error from this representation. Okay, so the eventual statement I'll make is that this, for Q bigger than 0, this holds up to some relatively small error that will wash out under the KPZ scaling. Okay, so okay, good. So this hopefully explains a little bit about how to get from all the line ensembles, how to kind of reduce them to one line ensemble. Okay, so now I need to now tell you how to understand that one line ensemble. And the key to doing that is that these line ensembles, as I described to you before, these line ensembles, they are described by Boltzmann weights, by the Q boson weights, right? So you can kind of interpret the Q boson weights in terms of these paths. And what you basically get is that they'll satisfy Gibbs property of a bunch of non-intersecting Bernoulli bridges, which is kind of the Q equals 0 part, times some extra factor. Okay, and okay, so what you do now is you'll have to show that this line ensemble is tight under the KPZ scaling, which we do. And somewhat of a difficulty here is that you don't have the FKG inequality, which was first noticed by Corwin and Dimitrov. Okay, but now once you know that it's tight, what you can kind of show is that this Gibbs property here of non-intersecting bridges times this term will kind of just tend to 1. And in the limit, non-intersecting Brownian Bernoulli bridges should converge to non-intersecting Brownian bridges, right? Just because Bernoulli random walks converge to Brownian motion. Okay, so what happens here is that any kind of limit, you've shown tightness, and any limit point will converge to a family of curves that has the Gibbs property for non-intersecting Brownian bridges. And now at this point, there's actually a fairly general characterization result that tells you that if you know that the top curve of your family of bridges, of your big family, of your ensemble, has some kind of quadratic decay, then, and you have this Brownian property, that actually just uniquely pins it down as the Airy line ensemble up to some shift. So this was actually, a special case of this result was predicted by O'Quinian and Sheffield, and the translation invariant in extremal case. This theorem doesn't impose either translation invariance or extremality. That's pretty useful for dealing with discrete models for which you don't have translation invariance. Okay, and the consequence of this, so you know that any limit point has the Gibbs property of Brownian bridges, and you furthermore know that any such thing has to be the Airy line ensemble, so that pins it down. Okay. Yeah. So I will skip the proof of the characterization and quickly summarize. So we analyzed the scaling limit of the colored ASEP through the colored stochastic 6-vertex model. We did that by first, it basically consisted in 3 steps. The first was in matching those into the top curves of a colored line ensemble. The proof, unfortunately, I didn't get to it, but it's a very quick consequence of the Yang-Baxter equation. The second step was to identify all the higher line ensembles, just in terms of the first one as an LPP problem. And that kind of proceeded by looking at the weights a little bit more carefully. And the third was to show that this line ensemble converged to the Airy line ensemble, which involved a tightness statement and then a characterization. And you might ask, how general is this procedure? So the third step is actually pretty robust. The second step, if you have the first step, is pretty robust. So you might ask about when exactly can you map these colors, these models into a colored line ensemble. So in the same paper with Alexei, we did it for a bunch of other models. Basically, it's kind of a seed model up here, which almost the same proof works. It's kind of some colored version, some fused stochastic model. And that actually degenerates to a lot of other models that one can study for which has this 0.1. So I just talked about these colored stochastic 6-vertex model. You also have a lot of the polymers, including the KPZ equation and some last passage models. You have the beta polymer, which I actually don't know how to analyze with RSK, and you have some other things like QTASEP and the QPNG. So with that, I'll stop there and thank you for your attention.
Except for color K-set, there isn't non-form. But for the transition probability for K-set, there is like determinant of form.
Wait, uncolored or colored?
Color. Because you can recover transition probability from color K-set.
Yeah, I mean, so what I was trying to say was that I have not seen any work that,
I'm wondering if you can get that formula from this mapping.
Yeah, I don't know offhand if you can get, well.
The principle is coded there.
Yes. in principle. Yeah, I agree that that's a question. I don't have a good answer for you at the moment. Yeah.
Other question. What happens to all these ensembles on the dual side of the ASEP?
Oh, so okay, so not much actually. So the one thing that makes them a little bit more confusing is that this ASEP, the stochastic subvergence model, both the x-axis and the y-axis are discrete, right? But for the ASEP, you can think of the y-axis as being continuous and the x-axis as being discrete. So what will happen is that this line ensemble, the first n sites would just be discrete, but above that it will kind of be continuous. And these paths, they can now exit according to kind of, you think of them as exponentials. So like kind of they'll originally start exiting as discrete, like in a discrete way, or in the kind of the bottom half of it. But on the top, they'll kind of start exiting at continuous locations. So that's what makes the story a little bit more complicated. Yeah.
All again.